So good morning, and thank you everybody for showing up during this lovely weather. I'm still drying up from my walk from the hotel. So not quite as scenic as Eduardo's view from Urbana, but this is view from my window at UBC. So if you ever come, you can enjoy this kind of view every morning. I'm going to talk about a topic that is new for me. So nothing is published. There's 2 preprints out there, and the work is done by my students and my postdocs. One of them, Nicholas, is here. I'd like to give a shout to the funding agencies, and especially CFAR, which is Canadian Institute for Advanced Research. And the reason is CFAR is this organization in Canada. Some of you are familiar with it. It's been around for nearly 30 years, and it organizes these annual meetings, which are very similar to this meeting. So I'm kind of feeling quite at home. And they are similar in the sense that there's very few talks and a lot of time for discussion. So I love that, and I want to give a shout to the organizers. Thank you for inviting me and setting it up like this. Okay, so altermagnets and superconductivity. I first learned about altermagnets from Nicholas when he came back last year from the DFG meeting, and he said, oh, it's everything about altermagnets. So I read some papers, and it immediately struck me when I look at these Fermi surfaces that are spin split. I started thinking, these are metals, and at low temperature, metals like to go superconducting. So what kind of superconductivity might occur in this kind of spin split Fermi surface? And if you think about this for a minute, you immediately realize it's going to have to be unconventional, because you cannot simply form conventional spin singlet Cooper pairs, right? Spin singlet Cooper pair has spin up, spin down, momentum plus k minus k, and that you just cannot form, because if you want to pair electrons with opposite momenta, then they have to have same spin, right? And that's quite clear from this picture, and it's also true in 3-dimensional situations. So interesting question, right? And the answer is the most natural pairing here would be equal spin odd parity, and this has been mentioned by some of the speakers already. And here's the hypothesis that I made. The pairs should look like this: 2 spins up. And of course, it has to be, the spatial part has to be odd under inversion. And I guess that it has to be this chiral p wave, because it gaps uniformly the whole Fermi surface. If you just had one of these components, px or py, it would be nodal, and that would be less, you would gain less condensation energy. And then I asked my undergraduate student, well, let's just do a calculation to see what happens. And we take a very simple model, this effective one-band model of an altermagnet that we've seen many times, and a similar one in 3 dimensions. And we just add a weak attraction on the lattice. And because we want to give equal chance to singlet and triplet, we use finite range attraction, which on the lattice is attraction between nearest neighbors, right? In order to get something else than S-wave, you need to have a finite range attraction, simply because your pair has to have some structure in real and momentum space in order to be odd under inversion. And then you can just go and do a completely standard calculation, derive gap equations for the singlet channel, for the triplet channel, and you can test the chiral triplet, non-chiral triplet. You can do D-wave, whatever you want. It's all just these kinds of equations, and even an undergraduate student with a little bit of skill can solve these, and here are some sample solutions. So let me guide you through this. So what we have here is, so this left panel is for a 2-dimensional model of an altermagnet. And we solve these gap equations for critical temperatures in singlet and triplet channels. Singlet is in orange, triplet is in blue, and we plot them as a function of this spin splitting eta, right? And the result totally makes sense if you look at it. At 0 spin splitting, you have just an ordinary non-magnetic metal, and you find that spin singlet S wave has the highest TC. It wins, and that's just a statement that most superconductors that we know are spin singlet S wave, right? That's all right here at 0. However, and there's a TC for chiral P wave, but it's lower. And again, we don't know that many P wave superconductors in ordinary systems. However, as you crank up this eta, you start splitting the Fermi surface, the S wave singlet just dives like a rock, and P wave is pretty much unaffected, right? So that's just a consequence of this intuition that I presented on the previous slide. You cannot form, in this situation, when you have spin split Fermi surfaces, you cannot form these singlet Cooper pairs. They are energetically unfavorable. And the place where this goes to 0 is roughly when this eta is equal to the size of the superconducting gap. So in real altermagnets, you're deep in this region, right? Because spin splitting is hundreds MeV. Typical size of superconducting gap would be few MeV, right? So you're really deep in this region. This triplet P wave wins. You do the calculation in 3D, and it's basically the same result. And I'm just showing one set of parameters, but it always looks like this. The fact that triplet wins is kind of universally valid, and that's the main message. And of course, we're not the first people to notice this. When we dig into the literature, there's several papers. I'm showing this one from 2023, where they also, these authors add spin orbit coupling, but they also conclude near 0 spin orbit coupling, it's P wave instability. So, you know.
11-year-old work that I have.
Yes, I'm sorry, I was not aware of that work, so I will next time cite it as well.
The competitor is actually an inhomogeneous, essentially a pair density wave.
Yeah.
And it has to be in the D wave channel. And you could also have D wave superconductivity. Yeah. So it's actually a bit more, it's richer than this. Now our calculation Pomeranchuk, but morally is similar because we had to stay close to this, to the point where the altermagnet appears.
Yeah, yeah.
As a control parameter.
Yeah, I hear you. Right after your talk, I actually went back to these equations and just changed this form factor to D wave, and it turns out it behaves similarly, dives down and starts a little lower. So again, maybe for different parameters, it could be.
Because it peaks. Wave vector.
Yeah, yeah.
Unlike the the S wave doesn't have a peak at
that is probably true. We haven't really scanned the whole finite momentum.
If you just look at the pair correlation function, essentially.
Yeah.
You see that.
Okay, I will have some comments about that later, but thank you for that comment. Okay, so for the rest of the talk, I will focus on these P wave channels, and again, this is something that has been mentioned already. So within this non-relativistic limit, when spin up and spin down sectors are decoupled, there's actually 4 different ground states that are degenerate. And basically what you can do, you have a spin up, and you have 2 different chiralities, P plus IP or P minus IP, and the same 2 possibilities for spin up, which makes for these 4 possibilities. And as an aside, all these are topologically non-trivial, right? So for instance, when you have the same chirality, then the superconductor has non-zero Chern number, either +2 or -2, which translates into these chiral edge modes. So this is a spectral function evaluated at the edge of the sample. There's actually 2 edge modes, but they lie on top of one another, so you cannot see them. If you have opposite chirality, then it's also topological. You have helical modes, they propagate in the opposite direction. This is actually stable, so when you have a Chern number, then you cannot get rid of this edge mode by any perturbation that does not close the bulk gap. And we tested that if you add some spin orbit coupling, these chiral edge modes persist. They are slightly resolved here, so you can see that there's actually 2. However, these helical edge modes, they are not really protected by anything. So as long as you allow some spin flip processes, there is a small gap opening up in these edge modes. However, and that has been also mentioned in the literature, this retains higher order topology. So if you put this material now on a finite sample with corners, there will be corner Majorana zero modes. And again, this has been mentioned in the literature. This is not something that we discovered ourselves. Okay, but what I'm really interested in and what I want to present today is this idea of persistent spin currents. This is interesting perhaps to people who work in spintronics because they are interested in transporting spin over distances, and this is always tricky in dissipative normal metals and semiconductors because spin current is not conserved and it decays. In a superconductor you can have a different situation, as I will show, and the fact that you can have spin polarized supercurrents, it's kind of obvious just by looking at the fact that you have two separate condensates for spin up and spin down electrons, right? In this non-relativistic limit, Hamiltonian looks like this. So you have a spin up block, spin down block, each superconducting, and they are decoupled, at least in this ideal limit. So you can imagine setting up a superflow in your spin up component and no superflow in spin down component. So you would have a fully spin polarized current. So that's kind of obvious at this level. Now the question I want to ask and answer to some degree is the following. So first, what are the situations where one could actually generate these type of spin polarized currents? And second question is, if we go away from this ideal limit, if we add a little bit of spin orbit coupling or some magnetic disorder, which puts some perturbation here where these zeros are these phenomena robust with respect to those spin flip type perturbations? So that's what I'm going to do. And the first question, I will give you several specific situations where one could actually see these phenomena. So the first is a kind of thought experiment which perhaps actually can be realized in a lab. Imagine you put this spin triplet superconductor on a ring and you thread some flux through this ring by applying magnetic field. And I'm going to try to convince you that for a particular value of this flux, you can actually have a pure spin supercurrent orbiting this ring. And this is, we can do this within microscopic theory, but that's more complicated. So let's work within just a simple Ginzburg-Landau. I describe this with two order parameter fields, one for spin up, one for spin down condensate. And each of them is subject to just the ordinary Ginzburg-Landau free energy like you find in any textbook. And if you have some of these spin flip processes like spin orbit coupling or magnetic disorder, then these can be coupled. And to leading order, the most important term is this Josephson type coupling, which you can read as a spin up Cooper pair being flipped down to a spin down Cooper pair by one of these perturbations. So that's the game that we're going to play. And as a first step, I will just disregard this, consider completely non-relativistic clean limit, and analyze the situation. So what I want is to find out what kind of currents will flow in this ring as a function of this applied magnetic field. And again, this analysis is completely standard. You open Tingham's book from 40 years ago, and you can almost just copy these equations, except he only has one spin singlet order parameter, so I'm generalizing it to two. So this would be the current density that you get from this free energy. And the only thing that we need to know for this analysis is that these order parameters psi have to be single valued as you go around the ring. What that means is that the phase of each, of these order parameters can wind by integer number of 2 pi, right? So it can wind 0 times, once, twice, or any integer number of times, and that leads to a constraint on what the total current can be. Namely, what you find is that the current in the ring is simply given by this. There is some prefactor which depends on all sorts of constants, but then there's an integer valued vorticity which can be +1 or -1, and then there is magnetic field which comes through the flux through the ring divided by the flux quantum. So that's the value of the current, and it can only have those values in equilibrium, right?
Can I ask a stupid question? Why there is no interaction between the magnetic field and spin? Even if you have thank you. Even if you have non-interacting channels, so I understand that here you take into account the orbital interactions, but still you can have spin.
Yeah, thank you. Thank you for that question. So to make things simple, I'm considering this idealized situation when I imagine that the flux only goes through the ring in the empty space, right? In that case, there is no interaction with spin. In reality, in a lab, one would, this would be some tiny microscopic ring. You would apply magnetic field. In that case, you would have the Zeeman effect. It is a small effect. We can estimate what it will do. It will split some degeneracies, but as long as the field is not strong, it will not be a huge effect.
So the coupling constant to the gauge field is E, right? And which is the same for both spin species. So can you, I'm struggling with the
okay, excellent question. So that's precisely why both channels, both currents for spin up and spin down depend on the magnetic field in exactly the same way, right? However, still, there are two different condensates, so these ends can be different, right? So that's where the whole business will be actually.
Okay, that's good. Perhaps a stupid question. Does the superconductor display the Meissner effect?
Yeah.
So it does.
It's flux quantization basically, which is related to the Meissner effect.
So it will expel the flux. If there's no hole in there, it's just a solid piece.
If it's a solid piece, it will expel the flux. Yeah, sure. Or if it's strong enough, yeah.
Still be type 1, type 2.
Yeah, and I'm assuming it's a type 2, but
A system like this with two complex order parameters can host half orbices also.
that's true too. Yeah.
If you have essentially a system with two complex order parameters, you can have fractional vortices, half vortices.
That's true, but at the level where these two order parameters are completely decoupled, then they each have to be single valued.
Once you put the D, then they are not.
That is true.
Okay.
Yeah, that is true. So that's why I'm taking this simple case as a first example, because I don't want to deal with all that complexity right away.
The two different n sigmas will give you fractional vortices in the end. If you choose one to be...
Yeah, we can view it that way. And that's exactly the interesting, that's the interesting part.
Yes, you have them here.
Yeah, okay. So I can write this free energy completely in terms of this current for spin up and spin down components. And it can be written like this, in this form. The first term is the superflow energy. Lk is called kinetic inductance, and again, it's just a bunch of constants that I can write, but I don't want to complicate things. And it simply comes from this gradient term. It's just the cost of pushing the current through this superconductor. The second piece here is just the magnetic energy coming from this last term, and it's basically what we teach students in first year E&M. When you have a current flowing in a ring, it produces magnetic field, and that costs electromagnetic energy. And notice that these two terms have different structure, and this is because only electric current gives you magnetic field. So electric current is spin up plus spin down current. If you don't have electric current, then you don't get magnetic field, whereas here I have a sum of the squares, because each of the currents costs me this superfluid energy. Okay, so now in thermodynamic equilibrium, I have to find the minimum of this free energy, and I will rewrite it on this page. And the only thing that I can actually vary is these integers now, right? That's my only degree of freedom. The superconductor has to decide what vorticity to put in which channel, and this is almost the high school level easy. So here's the result. this is these various lines correspond to various vorticities. So these numbers correspond to these integers, n up and n down. For instance, this parabola is when there's no vorticity at all. The energy just rises quadratically. And the interesting piece is, as Daniel pointed out, the one here in red where there's different vorticities, either 0, 1 or 1, 0, which are degenerate in this limit. If I included Zeeman effect, they would be slightly split. So that would be the effect of the Zeeman field. But importantly, and this is the result of this magnetic inductive energy, there is a region near half-flux quantum where this is energetically favored. And this is simply because when I have unequal vorticities, actually these two spin currents are opposite. Spin up goes this way, spin down goes in the opposite way. And so electric current actually cancels. That produces no magnetic field, and that's why this situation wins. So this is kind of interesting because this is exactly a situation when I have pure spin current flowing in this ring. Conclusion is here that near half-flux quantum, I will be sitting on this red branch, and I will see a pure spin supercurrent with no charge current. So for a while, we're thinking, how do we detect this? And there's a number of schemes in spintronics how you can detect spin currents, but in fact, you can detect this by a purely magnetic measurement. Imagine you just measure magnetization, and it's just a derivative of this free energy in the minimum branch, and it would look like this. It would first rise, and then unlike in conventional superconductor near half-flux quantum, the magnetization will be tiny, near 0. And that's your signal that there is only spin current flowing in the ring with no charge current. So in principle, this could be detected purely magnetically without any fancy spin current detection. Okay, so now one can ask this question. If we reintroduce this coupling between the two order parameters, will this remain stable? And one can analyze this. I don't have time to go to detail. Basically, this term acts as an internal Josephson coupling between the two condensates. So it wants the two phases to be actually always the same because that's what minimizes this cosine term. And you will find that as you crank up this d, basically this red curve goes up. So okay, I don't know why this happened. Sorry about that. Yeah. I'm sorry. So basically, one will lose this regime when this coupling is strong enough. This red curve basically goes up, and then it would start behaving as a usual normal superconductor. So only close to this relativistic limit, one can observe this effect. Eventually, it goes away, and that's kind of natural. And again, once we have some specific candidate for this, then we can discuss how large this is and how far we can go. Okay, a few other questions, and I will go through this quickly because I'm running out of time. So one can ask. If I inject a spin polarized current into this kind of wire, will it be stable when I have this coupling between spin up and spin down? And it turns out that it's going to be stable in some sense. You can drive this kind of spin current, and when you analyze this, you find that the spin current component that goes through a wire is proportional to the gradient of the relative phase between the spin up and spin down condensates. And you can derive equation of motion for this relative phase, which I'm going to do here. And this is a kind of amusing situation. So in this geometry for a wire, the equation of motion for that relative phase looks like this. And it's exactly mathematically equivalent to an equation of motion for a mechanical pendulum in gravitational field, which we know how to solve. And critically, it's an undamped pendulum. There's no damping term, so we know what the solution is. The pendulum either oscillates like this or it goes like that, but there's no decay in oscillations. And in complete analogy, spin current injected into this wire will simply undergo oscillations due to this fact that the condensates are coupled. And importantly, it will not decay. So for an arbitrarily long wire made out of this spin triplet superconductor, I could observe that spin current arbitrarily far away, and it should not decay. So that's a kind of another interesting result. So another effect that we came across is what we call spin current dynamo effect, and it's a superconducting equivalent of the spin splitter effect that has been introduced in the spintronic community, and it goes like this. So because we have these anisotropic Fermi surfaces and the anisotropy is opposite for spin up and spin down, the superfluid density tensor will also be anisotropic, and the anisotropy will be opposite for spin up and spin down. What it means is that if you apply, or if there is a flow of charge current in this material, there will be always concomitant flow of spin current. And when charge current is along x or y, spin current will go in the parallel direction. However, when you go along the diagonal direction, then the spin current will be perpendicular. And you know, this is what happens in a normal state, but in the normal state, those are dissipative currents. Here, these are persistent currents. So it's a direct analogy. And you know, I just wanted to see that it actually happens, so we did a simulation. So you know, we take a sample like this, we inject charge current in the y direction and observe whether there is a charge current flowing in the x direction. And this is a result, fully self-consistent calculation. This is the current resolved into spin up and spin down components. You cannot really see that much, but if I now change it into charge current, which is these blue arrows, and orange arrows are spin current, you can see that clearly there is this effect, right? So I'm forcing charge current from the blue electrode to the blue electrode, and then as a response, spin current flows in the orthogonal direction. And this is a persistent spin current, so this will again go arbitrarily far and will not decay. Since we're doing a real space simulation, we can investigate, is this robust against, say, magnetic disorder? And it turns out it's surprisingly robust. So here's a simulation where we put magnetic disorder on every side of our lattice, random magnetic moments. And you can see what happens in a fully self-consistent calculation. The colors are the order parameter amplitude, so they are quite disordered. Also, the currents, you see these arrows kind of point in various directions, but when you resolve it into charge and spin components, the effect is still there, even in the presence of fairly significant disorder. Here's the kind of summary plot where I'm plotting the total spin current in x direction as a function of applied electrical current in the x direction, and the three different colors here are clean, weak disorder, and strong disorder. And you can see that in all cases the spin current is just proportional to this charge current. The only thing that changes is that for strong disorder there's a large error bar. So when you put in this magnetic disorder, your spin current is no longer a conserved quantity. So it depends where exactly you measure it, and that's reflected in these error bars. But on average, the average value of the spin current is not really diminished by this disorder. So it's surprisingly robust. Okay. My last topics, I had quite a few questions, so I'm hoping I can take 5 more minutes to finish this. So, of course, at present we don't have any superconducting altermagnets, and that's a problem for all this theory. So we were thinking, are any of these effects going to still occur if we induce superconductivity by proximity effect? And the setup that I'm thinking of is to have a conventional superconductor like lead or aluminum or maybe high TC cuprate, to the extent that we can call that conventional, something that we know is superconducting. And on top of that, I put a thin layer of altermagnet, right? And any of these effects actually persist. And this is a non-trivial question, actually, because all these spin persistent currents depend on the fact that I have this equal spin triplet, right? And it's not clear how this ordinary spin singlet superconductor might induce a spin triplet superconductivity in altermagnet. That's a non-trivial question, so that's what we analyzed. And the answer is, again, within Ginzburg-Landau theory, where now I have 3 order parameters. Psi s denotes the order parameter in this conventional superconductor, and then I have my psi up, psi down order parameters in this altermagnet, which, however, in this situation are 0 in the isolated altermagnet, because I'm trying to discuss the proximity effect. Is this kind of a term allowed? That's the question. So this is the term that would generate proximity effect. If I can couple at linear order my conventional order parameter with these psi up, psi down, then that will generate non-zero order parameter in my altermagnet. And this is not clear that it is allowed because, of course, the spin singlet order parameter transforms trivially, say, under rotations, whereas this p wave generally transforms non-trivially. But again, if you think about that a little more carefully, you find that it all depends on which one you take. And if you take, remember there were these 4 degenerate states. If you take 2 of them, namely psi up, which has negative chirality, and psi down that has positive chirality in space, you find that this term is actually allowed because the total angular momentum in these 2 is actually 0, right? 2 spins up gives you +1, and p minus ip gives you -1, so the total jz is 0. And it transforms trivially under rotations, and so does this one. So this term is actually invariant and can be in this free energy, provided that I break inversion symmetry in this interface, because, of course, p wave is odd under inversion, whereas s wave is even. So the conclusion that I arrive from this symmetry analysis is that I can induce these triplet order parameters if I break inversion symmetry at the boundary. So if I have, say, some Rashba spin-orbit coupling at this surface, which is allowed because surface breaks inversion symmetry, then this should work. Okay, my last slide, we just put this to work. We write down the minimal model for this. So we model this superconductor as an ordinary BCS superconductor with some spin-orbit coupling. Again, we use the same D-wave model for the altermagnet, and we couple the 2 by tunneling, which preserves both momentum and spin. And then we solve everything. This is just 8 by 8 matrices, so we can solve this. And the interesting answer is that a kind of nodal superconductor emerges from this situation, which is a mix of singlet and triplet gaps. So here's the summary sketch of what happens. So first of all, my altermagnet, these crossings along the diagonal will be slightly split because there is a now Rashba spin-orbit coupling in the problem. So that's a first effect. Second effect is that a superconducting gap will be opened all over the Fermi surface. However, there's 2 different kind of gaps. In this diagonal region where spin splitting is small, there will be a predominantly spin singlet gap. In these regions where the spin splitting is large, there will be predominantly spin triplet gap. And they will be separated, actually, we find, by nodes in the gap, so there will be Dirac points. Thermodynamically, this will look a little bit like a D-wave superconductor, like a cuprate, because it has these Dirac nodes. In a D-wave cuprate, you have 4 of them in the Brillouin zone. Here, there will be 8 because there is 4 regions of each kind. And these will be visible in spectroscopy and thermodynamics. And another result is that the spin current dynamo effect will be present in this configuration as well, because you have these triplet gaps. And I will demonstrate that on my last transparency. So here's some of these concrete results. The first row here is a simulation of, suppose you could do angle result photo emission. You would measure a spectral function. In momentum space at 0 energy, you would find these types of Fermi surfaces. This is maybe not very revealing, but what's somewhat revealing is when I plot these spectral functions along these cuts in momentum space in frequency momentum space. So you see that at angle alpha equals 0, which is this white dashed line, I have a fully gapped spectrum, and this is the p-wave gap along the high splitting direction. Then at some critical angle, which for these parameters is 0.12 pi, the gap will close. That's the Dirac point. And then it will reopen again along this diagonal direction, which is the S-wave type gap. I summarize this finding here, which simply plots the gap amplitude as a function of this alpha, and various curves are for various strengths of coupling between the superconductor and the altermagnet. You can see that each of these curves has a node somewhere. So this would be the singlet S-wave gap, and this would be the P-wave gap that is triplet. You can calculate things like specific heat, for instance, and again, without going to too much detail, you find that at low temperature, the specific heat will go as T squared, which is a characteristic behavior when you have Dirac nodes. It is well known in cuprates, the low temperature specific heat goes as T squared in the superconducting state. My student, Nicholas, compiled some possible candidates. So this is known superconductors. This is known or suspected altermagnets. And here are the lattice mismatches for the two. This aluminum with one of the these Lieb oxychalcogenides, that has a very favorable low lattice mismatch, and we will do some DFT calculations to see if any one of them could be viable. So I'm hoping somebody will try this proximity effect. And finally, again, without going to too much detail, we also verified that by calculating charge and spin currents in this setup, that there will be this spin current dynamo effect, namely that when we apply electric or charge current in one direction, there will be spin current flowing in the perpendicular direction. In this case, the efficiency is kind of small. It's on the order of a few %, and this is because the charge current predominantly flows in the superconductor, so there's lots of charge current, but spin current is only generated in this one layer. So that's why this is relatively, the efficiency is relatively small. And this is all that I wanted to say, and thank you for your attention.
All right. Oh, all right. Let's start here.
Yeah, this very nice talk, Marcel. Spin orbit and the superconductor coupling. Most superconductors have spin orbit in them.
Mm-hmm.
And this has been an issue in the context of proximatizing an S-wave superconductor with a fractional quantum Hall or integer quantum Hall effect. So there is this experiment by Philip Kim and the Harvard group, where they have essentially a superconducting wire, which niobium nitride in that case, And they chose that because it has a high critical field. But this is actually coupled to graphene, which has essentially no spin orbit to speak about. Okay, so when they go into the integer Hall effect, they do get actually essentially an Andreas type cross Andreas reflection, which allows, so everywhere you would think that it wouldn't be possible to tunnel from a spin singlet superconductor into the edge state, say, of a Laughlin state, which is fully polarized. Or for that matter, for the nu equals 1, for essentially the spin. But in fact, you actually do see tunneling, and it's due to the spin-orbit coupling of the superconductor. So it's a very similar situation. And I don't understand why you need an additional superconductor in your. I think any superconductor of the type you have already will have the spin orbit.
Yes. Okay. Yeah. So that's that.
It will be an exception in some sense.
Okay.
So we have more, so we have less. Okay, but it will be an exceptional situation if there isn't one.
Okay, yeah, that's a very good comment. So I think generically, maybe I wasn't clear when I was commenting that I think generically there will be some spin orbit coupling, and that will enable that
and it is
tunneling.
in the superconductor, otherwise
Yeah.
you cannot do it. Okay? This is exactly what happened in this experiment.
Okay, yeah, that's a very good point. Yeah.
So thank you. So I was thinking about the ring, right? So there's and your spin splitter effect, and you could think now in the ring you also would have on the inside. So if you have the charge currents around, that you would get on the edges of the ring a spin polarization. But now thinking about that a little bit, that depends actually on how the D wave, the altermagnetic autoparameter, rotates in real so that do you assume that the say altermagnetic splitting co-rotates with the ring, or is rather this is given and the ring? So there are many that you couple to real space. So has to be a choice there, right?
Yeah. So that's a very good point. So I didn't mention that, but when we discuss this property in a ring, I was assuming without telling you that I'm using some G-wave type or I-wave altermagnet where the spin splitter effect does not occur, or else I'm thinking about multi-domain D-wave altermagnet where it will average out, right? If on top of everything you also have this anisotropy, then the situation is a bit more complicated, right? So one caveat underlies it all, that for the spin splitter effect to take place, and this is true in both normal and superconducting state, you have to have a single domain, right? Because if you have a domain where many domains in the sample where the red and blue are flipped, then this will just tend to average out, right? So
you might get some interesting spin textures on the sides of the ring.
Yeah,
You
yeah.
will still have it, but not.
Yeah.
It's like a geometric coupling that should be present naturally because of the anisotropic character of the magnet. Because it breaks rotation invariance.
Yeah.
Here first.
Wonderful talk. Thanks a lot. So I have a few questions. Questions whether you consider this already or whether you would be able to consider and help us, because there are people in our circles who are already doing experiments or trying to do experiments. So first question is, have you considered the inverse proximity effect? So the altermagnet killing superconductivity, because this is so far what we see when we make these bilayers with altermagnet and put a superconductor. What we see is the superconductivity is gone. So what is the optimal thickness of the superconductor and the altermagnet we should, or my colleagues should look for to actually have the proximity and not the inverse proximity effect?
Okay, so that's a very good question, and we already are seeing this. So it can be seen in this figure. So let me explain. I appreciate this question. So this is ordinary superfluid density as a function of temperature calculated for this situation, and this is combined superfluid density for the whole system, both altermagnet and a superconductor. And different colors going from dark blue to light blue and red are increasing coupling between the two, right? So notice what happens. The superfluid density at low temperature initially goes down, right? This is the zero coupling, this is small coupling. As coupling increases, it goes down. And that's precisely our inverse proximity effect. So first thing that happens is that superconductivity in the superconducting layer is being killed by altermagnet basically splitting the bands, right? So it's a relatively weak effect, but the superfluid density is going down. Eventually, when this coupling is quite strong, and I don't know if this is realistic, this is quite strong coupling, it starts going up. So that's this last orange bit. The predicted spin superfluid density actually just keeps going up uniformly. So for very weak coupling, it's very small, and then it keeps going up. So that means that somehow the spin splitter effect is proportional to the strength of this coupling, right? The superconductivity is being weakened, but still the spin polarization is increasing. So that's the result, if it makes any sense.
Yeah, but can you make some practical advice to experimentalists how to tune these things in their bilayers? You know, in terms of, is there an optimal thickness, for example, of the films where one effect? Yeah, yeah, yeah.
Yeah. So I would have to then know, what exactly are the materials that we're looking at, right?
And the other question.
Depends on the difference of the work functions.
Uh-huh.
Yeah, that depends on details as
these details can kill you.
Yeah.
Charge transfer, you have to know exactly how you cleave. I think it's very important to really talk to the experimentalists.
Right. Yeah. So like I said, we've been doing this for just a few months, and Nicholas will do some DFT calculations for specific examples. But if you have some specific materials that you're using in the lab, we would be extremely interested in knowing, and then we can.
Aluminum, chromium, antimony, aluminum, manganese, telluride. So, and this next question obviously is, what about G waves, right? If you replace the D wave with G wave.
Yeah, so for G wave without strain, as you know, you don't have this spin splitter effect.
No, but the proximity effect, just.
We haven't studied it, but I think the proximity effect would still work. But this is something that we can put into model, but we haven't done that yet. Yeah, sorry.
Thank you very much for the nice talk. Strain is not an issue because you will have a lot of lattice mismatch. So you can gain the strain by just making use of the lattice mismatch. But indeed, it's not going to be easy to have it realized, even if Niklas does the DFT calculations, because what is very important, the materials I see, the cleaving of the materials, it may kill you. Even if you do a nice DFT calculation, you really have to know how they are cleaving the system. Otherwise, you don't get the proximity effect, it's killed, or you have issues of charge transfer. And then you are doping, one of the two. But you also could investigate what happens upon doping. So I don't think that, it's really a very interesting suggestion. But it will take some time to really pin down the materials. But nice, very nice, yeah.
Another comment is, the mismatch was the criterion here, but I think in real life it doesn't really matter so much, because if you
Thickness.
Yeah, but depending on how you grow it, then you just get these islands that grow, and then if the lattice mismatch becomes too strong, they just stop. And if you do it,
you have grains, yeah.
Yeah, you're getting more. You have an extra potential to that, which will be the more potential.
Another thing actually with concerning this orbit coupling, we just put it because, as you were saying, we put the spin orbit coupling into the superconducting metal because it's there, but actually you can, from analyzing the charge potential from the DFT. Already just the inversion symmetry breaking from the interface gives you pretty strong spin orbit induced Rashba coupling that is, depending on the superconductor you pick, comparable to the gap size. So you get this effect for free, but then it's again as Jose is saying, it depends on the details, right? This is why it never worked putting a ferromagnet on top of an S wave. here I think you have one parameter less to tune because the chemical potential is not as important. But yeah, it's just a.
So related to what Eduardo was saying, that in principle you could also get these altermagnets or these superconductor, and as you said in the beginning of the talk, for these material combinations, what would be TC on the superconducting side and the altermagnetic side? So to speak, could you have like that both layers are already superconducting at the same time? And
well, I mean, yes, but then we don't need a superconductor, right? So this is a crutch because we don't yet have a superconducting altermagnet, so we're trying to induce superconductivity in a metallic altermagnet. And to answer your question,
the superconductor is very strong.
Yeah. So we're assuming this is a good superconductor, and it might even be possible to use a cuprate, for instance, which has high TC, large gap, and we're thinking about that as well. So TC depends on what you put in. If you put in aluminum, then it's
but for the altermagnets, you don't have a predicted TC for a superconducting transition, or do you?
No. I mean, as far as we know, again, none of the altermagnets are superconducting. And as you may know, predicting TC of any material is a tricky business, and I'm not going to enter that business in my old age.
Where the altermagnetic ordering temperature is much lower than the superconducting temperature. That's maybe where your question is. So.
But normally it's quite the opposite, right? The nail temperature is a room temperature or something like that, whereas TC of superconductor would be.
But then it's less likely that the altermagnet kills the superconductor, right? The superconductor is much stronger.
Okay, well, oh yeah. So what you're thinking is having a weak altermagnet, so to speak, so that the spin splitting is not that large. It's an interesting suggestion. Yeah.
The iron bromide is actually very weak spin splitting.
Mm-hmm.
So just a comment on materials. You may be better off if you consider one of those two-dimensional altermagnets that are actually ferroelectric. And I don't know if Libor is around, but he had a list. Didn't you have a list of those in your paper? Because then, because it's already Briggs inversion symmetry, you're going to get a monodomain when you put on. You should get a monodomain when you put on there, right? Which is another problem. And I think this could, and I think that he had the two-dimensional ones, which, probably you're gonna have better surfaces. So that's just a suggestion. Yeah, and I think he had. I mean, he can speak, but anyway. So that's just a thought.
Okay, thank you. That's an excellent suggestion.
Okay. Good with that. Okay. Maybe one final question. Because
just follow up on the.
This is why I'm still.
Just to follow up on the G-wave.
Well-established schedule, baby.
But so the G-wave would be interesting, I think, because you're saying you get this helical P, right, from the D-wave altermagnet, and the question will be, what do you get from the G-wave?
Okay, yeah, it will be different, and I don't know exactly how different it will be. Yeah, we want to do that. Yeah.
Okay.
Sorry, yes, apologies. So you talk about altermagnets. What about anti-altermagnets, where the polarization is K minus K antisymmetric?
Okay, so this is exactly what I'm thinking about right now, and there might be some very interesting superconducting physics as well, but we haven't done any calculations yet. Thank you for that suggestion.
Let's have